So now we've kind of covered all of the integration techniques that we want to go over. So we have the tools now to evaluate a broad class of different integrals. So like I've said, integrals can be tricky. So there's a lot more out there. A lot of times it's hard to even evaluate an integral, and we have to rely on some kind of approximation method, or maybe just using a computer program or something like that. So regardless, now we want to look at some applications of integrals. So these are going to be some things that we can use integrals for. So like we've already seen some practical purposes of it. Like for example, if we integrate a velocity function, we get the position function, right? And that can be any kind of, like, if you integrate any kind of rate of change function, it will give you back whatever thing was changing, right? So that can be applied to a lot of different things. In this video specifically, we want to look at what we call the average value of a function. Average value of a function. So we have this idea of average, of course, right? Where, like, for example, on a data set where you have a data set and you take the average value, we of course know what that is. But the function should have an average value as well. And it would be easy to do if the function was like a discrete set of points. You know, then we could take the average of the points, kind of like the midpoint formula, basically. But what about if it's a continuous function, right? Then it's not so straightforward to do that. So that's where integrals come into play, right? Integrals can help us deal with these continuous functions, so no different here. So I'll just write down what the average value of a function, the definition is. Okay. So the average value of a function f on an interval a, b is given by f, and then sometimes we write the subscript av for average, is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay. So you're taking whatever the integral is over that interval, and then you're dividing by the length of the interval, which is given by b minus a. Okay, so hopefully not too surprising. Like, it's one of those things where maybe you wouldn't think about it, but when you see it, I think the idea is kind of intuitive, right? You take the area of the on that interval and then divide by the length of the interval, right? Now, if you notice, this is actually just like the average rate of change of the antiderivative, right? So if we consider the antiderivative of f, which we denote by capital F, and we apply the fundamental theorem of calculus, we can see that this is actually just the average rate of change on that interval of the antiderivative. Okay. So again, average rate of change corresponding to the, in this case, the f, little f would be like the change, right? With a big F being the thing that's changing. So average change is given by this. So basically the same formula that we had before. Now we're just calling it the average value. Okay. So we can just look at a couple of examples here. Okay, so if we look at the examples, let's say we want to find the average value of 4x minus x squared on 0 to 4. Okay. So using this formula then, we're going to take the integral from 0 to 4 of 4x minus x squared And then we're going to multiply this by 1 over 4 minus 0. Okay, so just 1/4 in this case. So we just do the integral like normal, and then we end up multiplying by 1/4 at the end. Okay, so we get 1/4. This is going to be 4x squared over 2, so 2x squared minus x cubed over 3. And then we're evaluating this from x equals 0 to x equals 4. And the whole time we just keep bringing the 1/4 with us. Okay, so this is 1/4. 2 times 4 squared minus 4 cubed over 3. And then when we put in 0, everything's going to be 0. So that part's just going to be 0. Okay, so 1/4, 16 times 2 is 32. This is 64 thirds. Okay, so there's different ways you could do this. I'll just do the 1/4 part first. 8 minus 16 thirds. Okay, so you could just leave it like that, or you can make this 24 thirds minus 16 thirds. Okay, so overall we'll get 8 thirds. Okay, so the average value of 4x minus x squared on the interval of 0 to 4 is 8 thirds. Okay, so it's always a good idea just to kind of make sure that this makes sense. This function in particular, it's a parabola opening downwards. It has zeros at, it's going to be at 4 and 0. So if we just kind of imagine what that would look like, right? So you have a 0 here, a 0 here. The vertex is going to be right in the middle somewhere. So just to get a rough sketch of the graph, we don't need to like be precise about it. Then we can see that in this whole interval, it's positive, right? So that makes sense with the answer that we got. 8 thirds is almost 3, a little bit more than 2. So, I mean, I'd say it makes sense. Depending on where that vertex is, I would say our answer makes logical sense. Okay. Now there's another thing that we can do with this idea of the average value of a function. We can extend this idea a little bit more. Okay, so I'm going to give this a name after I write it, because I want you to think about exactly what it is, because you might recognize it. So if if f is continuous, continuous on AB, then there exists a number C in AB such that f of C is equal to 1 over b minus a times the integral from a to b of f of x dx. So rearranging this, and well, not even rearranging this, but just thinking about, again, the fact that this is actually just the average rate of change of the antiderivative on the right side. So this is capital F of b minus capital F of a divided by b minus a. Then you might recognize this as the mean value theorem applied to capital F, right? Remember that capital F of x prime, it would be lowercase f of x, right? and we meet all of the conditions for the original mean value theorem that we looked at back when we were looking at derivatives. So, this you might recognize this as the mean value theorem, and that's exactly what it is. It's the mean value theorem for integrals. Okay, so the mean value theorem for integrals. So oftentimes we like to write this a little bit differently. Okay, so instead of writing it as I have it written here, you'll often see it written as the integral from a to b of f of x dx is equal to f of c times b minus a. So on the surface, it doesn't look too different, but if we just think about the geometric interpretation of this, this is, remember, b minus a is the length of the thing that you're integrating on, right? So if we just think about a picture of this real quick. Okay, and then, so just think about like any function f, right? And you're going from a to b. So let's say that this has endpoints a and b. Then when we're integrating, we're finding the area underneath here, right? So the bottom of this would be b minus a, the length of it. And then we're saying that there's some number that we can multiply this by, some output of f that we can multiply this by that will actually give us that area. Okay. So it kind of suggests like if we just were able to find that number, we wouldn't even need to integrate in the first place, right? We could just do like a regular old length times width. But of course that's not feasible. We need to know the integral in order to find this number. But it just gives us a better geometric interpretation of what's going on here. So we can just look at an example that uses this real quick. Okay, so let's say that we want to look at the function f of x equals 1 plus x squared on the interval from -1 to 2. Okay, so this tells us, this mean value theorem for integrals tells us that there's some number, some output of f between -1 and 2 that we could multiply by the length of that interval to get the value of the integral. Okay, so specifically it tells us that if we look at the integral from -1 to 2 of 1 plus x squared dx, then that's equal to some number f of c times 2 minus -1, so 3. Okay. So in order to find this number, we need to actually evaluate the integral, of course. So we're going to do, we'll get x plus x cubed over 3, evaluated from x equals -1 to x equals 2. And then that's going to be equal to some 3 times some number f of c. So we evaluate the integral first, plugging in the bounds, and then we're going to end up dividing by 3. So on the left side here, we get 2 plus 8/3 minus a -1 minus a -1/3. Okay, so these will be pluses. So 8/3 plus 1/3 is just going to be 3. And then 2 plus 1 is also going to be 3. And then we're going to, so we'll get 6. Right? And then we're going to divide by 3. So we just get 2. And then that will be our answer. So in this case, the integral over the interval from -1 to 2 was 6. And then the length of the interval was 3. So that tells us that there is an output on that interval, which happens to be 2 in this case, which we could multiply by to get that integral, which was 6.